God, it's so funny. It's working. Here we go. Testing. Check. Testing. Just kidding. This part's not videotaping. It's just there. So this is my voice in case you're like don't want to be on camera. I know you don't care. Okay. There are 3 things we have to figure out before we take the test on Wednesday that are not really part of the note guide because I screwed up and I didn't put them on there. Here's the first one. Called rates of reactions. Specifically, how do you make reactions go faster? There are 4 ways. Imagine one of the reactions is sugar dissolving in coffee. How do I get that to happen as fast as possible? Stir it is an excellent example. Stirring is one way. That's how you spell it, though. That says stirring in case you can't read it. Why would that make the reaction happen faster? What is actually physically happening when you stir something? Mumble. Yeah, someone said up there that you have things bumping into each other, and that's literally what happens. More molecules bumping into other molecules makes reactions happen faster. So if you are stirring the sugar and it needs to come in contact with water to dissolve, well, as you stir it, you made more water molecules hit the sugar, and then it dissolves faster. Number 2, which I think someone also said, was increase the temperature. Dan's on fire right now. What happens when you increase temperature, which is essentially the same thing? How do the molecules move? They move faster, right? And so if they move faster, that means they bump into other stuff more, which means that the reaction, there'll be more contact and reaction sites to happen. So if it's sugar and you pour it into water, the water molecules are moving super fast if it's hot water, and then they start to dissolve faster because there's more contact. Another way you can get more contact is to increase surface area. Sugar cubes are not super popular anymore, but they used to be because it would be a certain amount of sugar every time. So if you want your coffee with 5 sugar cubes, then that would be like universal. Like if you went to someone's house, they could put 5 sugar cubes in and it would taste the same, as opposed to like a teaspoon, which can be like overflowing, or you can like level it off. You know what I mean? But a sugar cube is always the same size. Oh yeah, they're the best, right? Now sugar cubes dissolve very slowly because the only part of the sugar cube that's exposed to water is the outside. And so, did I say melt? I meant dissolve. Oh, good. And so, when you put them into water, water can only get at the outermost parts of the sugar cube. So if you break it up and put a teaspoon of sugar in, that would make it dissolve even faster because the water gets in between all the sugar molecules and it makes it dissolve faster. Even faster than that is take that sugar and grind it up like powdered sugar. That's got a ton of surface area. The particles are super, super tiny, and that means that when you put it in water, it dissolves like that really fast. So increasing the surface area means that you get more sites for the reactants to interact. And the last one is sort of random, but it's true and we should mention it. It's called using a catalyst. In a reaction, you've got reactants and you've got products. And a catalyst works right here to make this process happen faster. It's sort of like a third party that helps you get from the reactants to the products without actually taking part in the reaction. Okay, here, I'm going to say, I thought of something. It might be terrible. I'm just going to put it out there. You can judge it. If you're trying to have a transaction on the internet, if you want to buy some pants from the Gap, because you're 33-year-old male and that's where you're buying pants now. So if you do that and you have slower internet, it might take a little bit of time, even though the end result is you still get a pair of pants, because that transaction might take longer or whatever. But if you have fast internet connection, something that helps you get from point A to point B, you still have the same end result, which is a fantastic pair of jeans, but it would happen at a faster rate because your catalyst is the internet speed. I don't know. It's a terrible example, but whatever. I said it. It's out there. We can't take it back. It's on tape forever. It just happened. Okay, that's one section. How to speed stuff up. There'll be a part of the test where you're just asked to say, how do you speed things up? Or actually, it'll be like, what reaction is faster? One that you stir, one that you don't stir. That kind of stuff. That's what you have to think about. Phase 2. There are 3 phases for this workout plan. Phase 2. What do endo and exothermic graphs look like? You're going to need 1/3 of a page. I don't know. We all write differently. It's hard to even estimate. I'm sorry that it's like the end of your life. It just sounds so terrible. Like it's, summer, this is the worst class ever. I want to know how much space I need. I'm going to make 2 graphs like this. Here's 1, here's 2. On the y-axis will be temperature. On the x-axis is time. On both of them. This one will be exothermic. This one will be endothermic. Do you remember the blue jug demonstration? With the fire, yes. What kind of reaction was that? Chemical. Yes, it was a chemical reaction. Now classify it as either exo or endothermic. Exo, right? It generated a lot of heat and energy. So what would you expect an exothermic graph to look like? Would the temperature go up or down? It would go up. So it usually starts like this, and then it goes up like that. Exothermic. Endothermic graphs, they require energy, and as a result, their temperature decreases, and so they look just the opposite. They start high and they end low. Now, if you wanted to calculate the change in temperature, you would just calculate, from here to there, that's delta T, right? What it started at and where it ended, same thing here. Just calculate from the beginning to the end, that's called delta T. But you can actually go through and calculate, change in temperatures for any reaction. If we have time, maybe on one of those days where we have packets to work on, maybe we'll do a little lab that looks at this a little bit. Excuse me. Okay. So exothermic temperature increases, endothermic temperature decreases. A graph would look something like that. Temperature would increase or decrease over time accordingly. Last one. But by far the most fun. State changes. Also called phase changes because you're just going between different phases, solid, liquid, and gas. Check out my cool graph. That light is not going to get the job done. Oh my gosh. Wait. Oh, this is terrible. No, it's over. This class is over. Everyone go home. Shh. Wait, hold on. What had happened? Okay, it's the best we got. When you have, this is a heating curve for water. Here it's a solid, which means that it's ice. Here it's melting. There it turns into a liquid. Here it boils or evaporates, and there it's a gas. Okay, but throughout the entire curve, what's the formula for water? H2O. Very good. Okay, why is it doing that now? Guys, has there ever been a worse day of this class? No. Except every day. Is it too much? You don't like it? You want to go sit in the hall or something? Man, I'm so glad I saw it. All right, anyway, so it's a solid here. And to get it to melt, what do you got to do to it? You got to put energy in or take energy out? To get it to melt, when you put it on your countertop, what happens to the temperature? It's different than the freezer, right? It's higher than the freezer. And so it's warmer on the outside than it is in the ice cube. And so where's the temperature flowing? Is it flowing into the ice cube or out of the ice cube? It's flowing into, right? Energy always flows hot to cold. And so, or heat always flows hot to cold. So as you put it into, when you're melting, you put energy in, so that's an endothermic process, okay? And then it becomes a liquid, and then eventually gets to a boiling point. Now when it boils, the temperature remains the same. That'd be at 100 degrees. So if you let your water boil for 20 minutes, it's still going to be 100 degrees. It doesn't change. While it's boiling, all the energy is going to breaking the molecules up and putting them into the gas form. And so that's where all the energy is. So it stays at 100 degrees until it's all gas, and then you can heat the gas up. But the gas isn't going to cook your pasta. Only the water will. So anyway, if you're going from left to right, all these processes are endothermic. From melting up to evaporation, all those two things are endothermic. Now going the other direction, right to left, if the molecules are moving really fast when they're a gas and they start to slow down and they lose their energy here, then they're going to become a liquid. That's called condensation, and you're putting energy. You're taking energy out. It's an exothermic process, going right to left. And then a liquid putting into ice. When you put ice in, or when you put water into the freezer, what's colder, the freezer or the water? The freezer is, right? So where does the energy flow? Say it other way. Right, because it always flows hot to cold, and the water is warmer than the freezer. So when you put the water into the freezer, energy is leaving the water and going to the freezer. That's exothermic, okay? Because it always flows hot to cold. So going left to right, it's endothermic. Going right to left is exothermic. Let me show you in a very simple to use table format why you need to know that and what that exactly means. Sorry, you okay, Nicole? Okay, I kind of scared you there. Let's start with endo, and this will be exothermic. The endothermic processes are ones that require energy. We already said that one of them was melting. When you're melting, you're going from a solid to a liquid. That's what that means. What is another phase transition or state change that you have to put energy into to make it happen? Yeah, that's what we do, but what happens when you heat water enough? You can evaporate it very rapidly, or you can boil it. So evaporation also requires energy. That's from a liquid to a gas. Now that's the opposite, right? So when you're going freezing, now you're exothermic. When you freeze something, you're going from a liquid to a solid. The molecules are moving really fast as a liquid. They're slowing down as a solid, so you have to take energy out of that. So it's giving energy away. That's the definition of exothermic. What's the opposite of evaporation? Condensation. Condensation, you're going from a gas to a liquid. The molecule's moving really fast, again as a gas, and they have to slow down and lose some of that energy to become a liquid. There's actually two more. They're not as popular. They're not as common. Does anyone know what going from a solid directly to a gas is? Nope. Dry ice does it, if that helps. Or disappearing? Yeah. No, but I like it. It's called, I forgot, sublimation. Almost forgot. That would have been embarrassing. Going right from a solid to a gas. What? No, it goes right from a solid to a gas. There's no liquid at all. That's why it's used for... They'll use dry ice for things like... how many of you guys do like when it's not Simon Delivers anymore? What's it called? Coburns? They deliver food to your house. They ship those in packets with like dry ice in them because the dry ice keeps it cold, obviously. Dry ice is just solid carbon dioxide. And at regular atmospheric conditions, dry ice goes right from a solid to a gas, which means there's no messy puddle to clean up at the end of the day when your truck is all empty and there's no like water in there, right? So it goes right from a solid to a gas, and the gas is fine. It's already in the atmosphere, so it's not a huge deal. So dry ice is like that. Also mothballs. You know, old people kind of smell like mothballs, right? You know what that smell is like? Old. It's like just old people. Back when old people were less old, they would put mothballs into their closets or their undies drawer or whatever. Because like certain, we don't call them undies, when certain bugs, moths, will eat their larvae, will eat your fabric, and you'll find like little holes in your shirts and stuff. And so mothballs are a chemical that kills moths, and it's a little solid. Well, it's called naphthalene. And then you put it into your closet or whatever, and then it goes right from a solid to a gas, which means there's no puddle to clean up, and the gas is what kills the bugs. And it has a really strong sort of smell that you would probably recognize.
Yeah, why would you want to put that in your underwear? It would make your underwear smell.
Yeah, but you wouldn't have any bugs in your underwear. Or holes. Well, that's why old people are different than you. It's actually, they're not used that much anymore because probably homes have become more, secure, and you don't have to worry about bugs infiltrating your house that often. It doesn't kill mice, I don't think. Maybe if they eat it, it would probably kill it. Is that true? Says who? Oh, okay. The opposite of sublimation is something called deposition. Deposition is going right from a solid to, backwards, a gas to a solid. It doesn't happen that often, but if you collected that dry ice gas and then cooled it down again, you could go right from a solid or from a gas to a solid.